Hello friends, today we are going to discuss the resistance calculation. So we just start with this resistance. They're basically like two arrangements, which is one is series, another is parallel. Now let's have a look both of them. I'll just draw a simple circuit. So that's the resistance here. Let's say there is another branch. So this is V, this is I, and this is R1, R2. Now let's just draw a series circuit as well. So that's a V, and that's I, that's R1 and R2. So you can see in the parallel circuit, the R1 and R2 are parallel to each other, so they branch out differently, like they are not in the same series, or we could say they differ, like there is a junction here. You can say point A and point B. So at point A and point B, they branch out as to resistance R1 and R2. Wherever in series, they just follow the same line of flow. So now let's say if you want to find out in Ohm's law, what we see is V equals to IR. Now this IR in this case, I would say, let's write it parallel. In this one I would say R equivalent. So what's my R equivalent here? So to find that, there is a ratio that you can remember. R equivalent equals to 1 upon R1 plus 1 upon R2. So that's the relation between R equivalent and R1 and R2. Now if you just do simple math, R equals to, so here I would say 1 upon, so this one is R1 plus R2 divided by R1 R2. You can write it this way, and that's can be written as R1 R2 upon R1 plus R2. So that's your R equivalent for parallel. Now let's say for series, so for series, the formula for R equivalent is just straight R1 plus R2. So you have to just sum it up, whatever you see in the series. So let's say, for example, I'll just modify the same thing. So if I just cut this one and put another resistance which is R3, then what would this one have been? It would be R1 plus R2 plus R3. Now in this case as well, like if you had another resistance like this, let's say R3, in which case 1 upon R equivalent would become 1 upon R1 plus 1 upon R2 plus 1 upon R3. So here, yeah, I mean, you can, it might sound a little complicated to just calculate this, because then it will be like R2 R3 plus R1 R3 plus R1 R2 divided by R1 R2 R3, and then you have to take the inverse of it to get the R equivalent. But I think when you have numbers here, I think it will look much simpler and it will be easier to calculate. So that's it for today, and next time I will probably look into the current divider rule and the voltage divider rule for this circuit. So I'll just give you the basic of it. Why do we need that? So let's say that's the current that's going through this parallel circuit. So if you see here, according to Ohm's law, the current that's passing to branch I1 from branch 2 I2 and from branch 3 I3, they wouldn't be same. They will depend on how much resistance they've been offered, and according to that they will flow. So the lower the resistance, the higher will be the current, and the higher the resistance, the lower will be the current. So however, the voltage that's applied to each branch is still the same, but the current that's passing through, that depends on the resistance that that they've been offered. So, and for the same thing that we can look into here. So here if you see, the current, the flow will be the same because it's the same branch. Like it's not branching out, actually it's just the same line of flow. But in here, like the voltage divides. So if you apply, let's say for R1, then R1 would not, let's say it's R1, then R1 I equals to V. And if you see, like this doesn't match, right? Because if V is the total, like EMF, or what you can say, um, like the voltage here, it will, then in that case it will become like R2I equals to R3I, which actually doesn't, so this is valid, but then they all equals to V, which is quite not true, because the V gets divided, and according to it, the rating of the loads, like it gets a part of the total V. But that's something that we'll look into next video, so please stay tuned, and yeah, please like and subscribe. Thank you.